Empire State Building, or maybe in a residential home, or those far, far away industrial factories, and ever wonder what keeps these buildings up? Well, I'll tell you. Steel beams. Steel beams serve as essential framework for these buildings, often differing in design to serve their job best, with an important job being bearing the vertical forces these buildings experience, of which two designs are commonly used. The question is of which design is better. This is why our experiment is about comparing the ultimate limit state of centrally loaded iron H beams.
Hello, I'm Marsack from Cosno High School.
I'm Romano, and I'm from Romano.
So to start, we're going to take you through some background information so that you can get well versed in the science involved with the iron H beams. Then we're going to go through our problem and hypotheses in our experimental design and procedure. We're going to talk about our data observations and the results we gained from this, and conclude and recap, give you some takeaways, and further research that still needs to be conducted. So to start, we have iron H beams right here. They both are comprised of a web, which is this vertical section in the center, and there are two flanges on either end that extrude off horizontally. The strong axis is perpendicular to the web area, and the weak axis is parallel to the web area. Here we have an I and H beam. They both are described with height or depth and base. The height is from the bottom of the bottom flange to the top of the top flange, and the base is just the width of the bottom flange or the top flange. For I-beams, their height-to-base ratio is 1.5, and for H-beams, it is less than 1.5. It could also be greater than 1.5 for H-beams. H-beams usually have a thicker web and a larger depth, whereas H-beams are going to have a thicker flange and a wider flange. Load is any type of sustained force onto some sort of structure for some period amount of time. And there are three main mechanical stresses you'll need to know. We have tension, where two parallel forces pull out from the center of the beam, compression, where forces push in towards the center of the beam, and shear, where a force is applied perpendicular to the beam. So if we apply a force to the center of the beam, this top section will experience compression, this center section will experience shear stress, and the bottom section will experience tensile stress. These combined create the experience of bending, and if we keep applying this force, eventually the beam will split apart and break. This is known as the ultimate limit state when it loses its load-bearing capacity. This is comprised of the shear area, elastic section modulus, and a second moment of area. Here are the formulas for each, and these all boil down to as height and thickness of the web increase, all three of these will increase. And combined, this means that the ultimate limit state will increase as the height and thickness of the web increase. Here is a 3-point flexural test, which is the type of test we used to figure out the overall strength of our beams. We have the loading pin, which applies an external force to the center of the beam, and two supporting pins, which apply a normal force and keep the beam in place.
So the problem statement in this experiment was to determine if there is a difference in the maximum amount of force a H-beam can handle compared to an I-beam when centrally loaded until the point of failure. We hypothesized that the I-beam will be able to handle more force when centrally loaded until the point of failure compared to that of a H-beam. In this experiment, we had used a vernier go direct tester to replicate a 3-point flexural test. And then once we had determined that, we had to find a way to produce the beam that was breakable but also consistent. We found this to be 3D printing. Once we had determined that, we had to scale the beams to be breakable but printable by the tester. And then once we had figured that out, we had to modify the beams to have equivalent cross-sectional area, which is to say when they were produced through 3D printing, there would be no difference in the amount of plastic used.
Is it just taking a long time to load? No, it's just not right. And it's probably because, let me see if the internet is bad.
So in our experiment, to replicate the 3-point flexural test, the vernier go direct tester was utilized. We had to find and once we had determined this, we had to find a way to produce the beams that was consistent but also breakable, which we found to be 3D printing. Once we had determined that, we had to scale the beams to be breakable and printable by the tester, and then once we have found that, we then modified the beams to have equivalent cross-sectional area, which is to say when the beams are produced, there would be no difference in the amount of plastic used that could influence their performance.
Alright, so here we have, hopefully a video. area.
Yeah.
Man.
Still the computer.
Not everything's hooked up like it should be.
No.
Oh yes, okay, so we have our beam in SolidWorks, which is the 3D modeling program that we use to make our beams. We have Prusa Slicer, which was our G-code compiler, and this basically just exports our 3D files into G-code, which is what these 3D printers use to know exactly how they're gonna print our beams. We're gonna export that G-code, spray down the printing plane, and wipe it down so that there's no dirt or dust that will interfere with the printing process. It's gonna start probing to make sure that it's printing in the right area, and then we're gonna stay around for a little bit, make sure it's starting to print the right file. And then eventually, once we know it's working, we're gonna close our printing area so that no dust or dirt gets into the 3D printers during the 17-hour long printing process. The next day, we're gonna come back and pull off this printing plane and give it a nice little bend. This is gonna pop off all of the beams. We'll remove them one by one, and then we'll take them over to our testing area where we are gonna remove the supports that were used for 3D printing so that they're ready for testing. So that's a complete beam right there. So here is our experimental setup. We have our Video Go Direct structures and materials tester, and we have a beam in the very top supported by those two supporting pins. We have this U-bolt, which acts as our loading pin, and that is attached to a quick link to a welded eye bolt directly into the force sensor. This is gonna send its readings to a laptop on the Veneer Graphical Analysis program. Now, once we have we have created all of our beams, we're gonna start labeling them. So then we will, so we can randomize the order that they appear. We're gonna read which trial number we're on, select the corresponding beam, and load that into our tester right here. We're gonna make sure that the U-bolt is nice and snug on the beam, but not applying a significant force on it. And once it's nice and secure in there, we're gonna start collecting data and lower the force sensor until the beam fails. Then we'll record the maximum force withstood and record that into our Excel for that trial.
So some things we noticed during experimentation was the amount of flex the beams went under when they were being tested, with the I-beams flexing a lot more than the H-beams. Another thing we noticed was their failures, as the H-beams always failed to do due to some breakage, whereas the I-beams always failed to falling over and never due to any breakage. Now we're going to look at the data distributions with the H-beam distribution above and the I-beam distribution below, with them both having no extreme outliers or skew, being approximately normal. As you can see, the I-beam distribution has a mean of 53.7 newtons, with the H-beam distribution having a mean of 127.5 newtons. But even with those numbers, the big thing to note is this large gap of 52.7 newtons, which shows no overlap. What this means is that there was a difference in the maximum amount of force withstood until the point of failure, with that being in favor of the H-beams. But to further confirm this, a two-scientific test was conducted, whose conditions go as follows: of large constant normality and randomization. The large constant normality condition needs either a trial size greater than or equal to 30 for each beam, or their data distribution to be normal, which was met as the data was approximately normal for both, and for randomization was met as each trial was randomly assigned a beam design. And now moving on to our statistical hypotheses, with our null hypothesis being that the true mean maximum amount of force withstood until the point of failure was equal for both the H and I beam, with our alternative hypothesis being, or the hypothesis we're trying to find convincing evidence for, that the true mean maximum force withstood until the point of failure is greater for the H beams than the I beams. And then using our data and our TNSPire software, return us this T distribution graph and these results. And return us a T value of 37.1, and using degrees of freedom of 19, return us a P value of approximately 0, and which was less than an alpha level 0.05. But what this really means is that there was no chance of seeing a difference between the observed means of the H and I beams of 73.8 newtons or more by chance alone. And what this allows us to do is it allows us to reject our null hypothesis as our P value was less than our alpha level of 0.05, and find convincing evidence for the alternative, or that the true mean and maximum amount of force withstood until the point of failure was greater for the H beams than the I beams.
So we originally hypothesized that the I-beams would withstand more force than the H-beams when centrally loaded until failure. But we were wrong. So we rejected this hypothesis. But why did this happen? So we looked at the second moment of area for the strong axis earlier, but there was also one for the weak axis. And this looks at the base and thickness of the flange. Now, this will increase as both of these factors increase, which will increase the ultimate limit state failure resistance in the lateral direction, or it will increase its lateral buckling resistance, in other words. This is much greater for H-beams and much smaller for I-beams. So this was what led to the early failure in I-beams due to the lateral buckling because it was so weak laterally or horizontally. There's also flexural anastropy, which is a ratio between the absolute strength between the weak and strong axes for an I or H-beam. And this basically measures directional strength and buckling resistance. It is approximately 1 to 2 for H-beams, and it is usually greater than 4 for I-beams. So for H-beams, their strong axis is roughly as strong as their weak axis, whereas for I-beams, their strong axis is much stronger than their weak axis. Past research by DiLorenzo and Associates looked at efficiencies across varying cross-sectional areas of different sizes and different ratios, and they too also found that I-beams were better suited for bending strong axis scenarios. And H-beams were much better for greater overall efficiency and had a much higher buckling resistance. So to recap, we thought that I-beams would be much stronger than H-beams, but we were wrong. It was actually the opposite. H-beams were much more resistant to lateral buckling, which meant that they were able to reach their ultimate limit state in this vertical sense. Whereas the I-beams always fell over and buckled laterally, so they were never able to reach their maximum potential in the vertical sense. And this is backed up by the gap of 52.7 newtons in the distributions in favor of the H-beams and our p-value of approximately 0.
So one thing we want to talk about now, some failures, some problems we had during early research, and things that can change future research. So one thing we had is problems with production. We had to find the correct scale. Again, as I said earlier, that was breakable by the machine. Additionally, with 3D printing, there's some problems that come with it when making the orientation or settings of it, which all affect the beam performance. Especially with traditional 3D printing, there's problems that come with layer lines and infill. So to remove those in future research, trying different methods of production that remove these in their entirety, such as resin 3D printing, could be used. Additionally, looking at those different scales of the beams to see if those did have any effect on their performance, on their efficiencies, would be another area to look at. But even with this, the bigger problem we experienced was the I-beams failing due to falling over rather than actually any sort of breakage, which is not really representative of what might happen in real life. So for future research, looking at reinforcements affected beam designs could be another area to look at, as they help prevent the buckling they experience, which could allow the I-beams to reach their true ultimate limit state rather than failing early and falling over. Additionally, looking at different flexural tests, such as the 4-point flexural test, could be another area to look at, as in real life, maybe it's not always one central force, maybe multiple, so this may collect more data on the ultimate limit state for these beams under different scenarios. And then finally, also looking at different models for the H and I beams, as we only use 2 specific models. For the H beam, we'd use the HE100A. For the I beam, we use the IPE180. But there are many more models of that. They all differ in their features, from the flange size to thickness. So seeing how those affect the performance could also be another area. But even knowing all this, why did this research matter and why was it important? Well, I'll tell you. For construction workers and civil engineers, this provides knowledge onto which situations to use each design. For example, if you need a structure that requires extreme strength and rigidity from the steel framework, you want to use H-beams for that, which is important for things such as high-rise buildings and skyscrapers. But if you need your building to have a little bit of movement or flex, or you need the beams to be a little more shock absorbent, the I-beams would be better, which is important for things such as bridges or stadiums, which allows these groups to save on money and resources as they aren't choosing the incorrect beam for the incorrect design. Additionally, this helps prevent failures in buildings, increasing their stability and allowing for more safety.
We would like to acknowledge Mr. May for helping us with the 3D printing process and allowing us to use his 3D printers. We'd like to thank Mr. McMillan for helping us with the physics involved in this research, and Ms. Sobolski for helping us with the formatting and statistical analysis involved in this research. Here are our references. Thank you for listening.